In this video, we focus on dielectrics, mainly on their effects when we put them in between the plates of a parallel plate capacitor. Then we will briefly analyze what is the dielectric breakdown. So a dielectric is mainly a non-conductor material. So it could be made of polar molecules that, if you remember, have small dipole moments like the ones shown in this picture, that are oriented quite randomly if there is no external electric field applied. However, if we applied an electric field, the dipoles are going to orientate in the sense of the electric field. So here in E sub 0 is the external electric field being applied to the dielectric, and here you can see that the dipole molecules have orientated. If the dielectric was not made of polar molecules, the application of this external electric field is going to produce induced dipoles, and it's going to orient them. In any case, what we have is that this alignment is going to produce a net electric field within the dielectric that is going to be opposed to the external field being applied. So inside the dielectric, the total electric field is going to be weaker than the external electric field applied. So when we put this dielectric in between the plates of a parallel plate capacitor, the effect is going to be to reduce the electric field inside the dielectric. So this we can show it here. These are the plates of the parallel plate capacitor, and these molecules, these dipoles, represent the oriented dipoles in the sense of the electric field. So if you see, this orientation is going to leave several charges in the borders of the dielectric material, which are called bound charges. So another representation, we can call E sub 0 to the electric field externally applied, which would be the external electric field in the whole space if the electric wasn't there. However, when we put the dielectric inside the dielectric, the electric field is not equal to E sub 0, but it's equal to E, which is smaller than E sub 0. So we're going to call the dielectric constant the amount by which the electric field is reduced inside the dielectric when the external electric field is applied. So this dielectric constant, represented by the Greek letter kappa, is always bigger than 1. This is going to change the overall capacity of the capacitor if we put a dielectric, because the capacity of the dielectric, the capacity of the capacitor can always be calculated as the ratio between the total charge we have in the capacitor divided by the difference of potential between plates. And in this case, when we have a dielectric between the plates of the capacitor, the electric potential is going to be E times D, where E is smaller than E sub 0, and it's equal to E sub 0 divided by this kappa. So the capacitance is going to be Q divided by E sub 0 D times kappa, which is this here is the original capacitance. So the final capacitance of the capacitor when we put a dielectric constant kappa is increased by this factor kappa. So the final capacity for this parallel plate capacitor with a dielectric is going to be given by this expression, where A is the total area of the plates, D is the distance between the plates, epsilon sub 0 is the electric constant, and kappa is the dielectric constant. So in a way, we can put these two constants together: the permittivity of the vacuum, or the electric constant epsilon sub 0 times kappa, and call it just epsilon, which is going to be the permittivity of the dielectric. In this table, you have for several different materials their dielectric constant. This permittivity of the dielectric also helps us to formulate expressions that we had seen before using the permittivity of the vacuum, but for different materials, for different dielectrics. So, for instance, now we have that the capacity is going to be epsilon times A divided by D instead of epsilon sub 0, and this is also going to be applied, for instance, to the energy density, which is going to be 1/2 epsilon times the square of the electric field. And also we can reformulate Gauss's law for a dielectric by using epsilon instead of epsilon sub 0. If you notice on the third column of this table, you can see a new variable that is called the resistance of the dielectric, which is the maximum electric field dielectric can bear before it breaks down and is ionized. So this brings us to the dielectric breakdown, which is the ionization of the dielectric when an external electric field very, very strong is applied. So for instance, for the air, the maximum electric field that can stand is 3 megavolts per meter, and this is called the dielectric strength. For electric fields above this threshold, the air becomes ionized, and this is because the ions present in the air, when you apply such a great electric field, they are strongly accelerated and they collide with the different molecules, forming new ions, and this is a change reaction that produces an electric shock. An example of this electric shock would be a spark, or it could be also the lightning. The lightning we see in clouds is the breakdown of the dielectric of the air, the dielectric breakdown of air. If you've noticed, perhaps you've noticed that it's easier to see a spark when the material has a sharp edge. This is called the sharp edge effect and can be explained in the following way. Imagine you have a conductor like the one shown in this diagram. So it has an edge A that has a sharper edge than edge B, which is much less sharp. So I'm going to show you that there is a relationship between the electric field produced in the surroundings of edge A and the potential difference. The electric potential of the conductor. So if you remember, a conductor in electrostatic equilibrium has the same potential everywhere. So we can approximate this area here. This area here with like it was a spherical conducting sphere. So for a conducting sphere, if you remember, the potential was related to the charge and the radius. You can see the former slides if you want. So this is equal to 1/4 pi epsilon sub 0 q divided by r. If we multiply and divide by r, then if you see here, we have, this is sigma, so we can put here sigma r divided by epsilon sub 0. This is sigma is related, the surface charge density in the area of A is related to the potential and also to the radius. Okay, so in region A, the radius is smaller than in region B, so the surface charge density is going to be bigger. And if you remember, the surface charge density was directly related with the electric field in the surrounding area, because if you apply Gauss's law, you can see that the electric field in the area very next to the conductor is given by sigma divided by epsilon sub 0. So this provides you with the measure that is going to be that E is going to be equal to V divided by R. So at both sides, A and B, the potential, the electric potential is the same, but R is much smaller in region A than in region B. So E in region A is going to be much bigger than E and the electric field in region B. And this explains why the electric breakdown is easier accomplished in a sharp edge than in a less sharp edge. Before finishing this video, I would like to show you just the problems you can solve, which is all of them right now. With this dielectric, the effect of dielectric comes into play in problems 9, 10, and 12.